Hello everyone, and welcome to our first recitation video for the Topological Data Analysis and Neuroscience course. I will be your TA for this course. My name is Nate Claus. If you want a little bit more background on myself or the head lecturer for the course, Dr. Alex McCleary, please see the introductory video we put up on YouTube where we just give a little bit of background on ourselves. So this, again, is the first recitation video. For this course, recitations will primarily focus as an enhancement to the lecture, where we discuss some of the topics in lecture either in more depth or go over practice problems or supplement the lecture in some similar way. Now, the first couple weeks will be slightly different in recitation because the first couple recitations will be largely disjoint from the lecture. So the first couple weeks recitations will be focused on reviewing prerequisite material that is particularly important to this course. In this initial week's videos, we will be covering some review of linear algebra. Again, linear algebra is a prerequisite for this course, so hopefully you've seen everything that we'll be discussing in these first few recitation videos, but if you need a bit of refresher, hopefully this will get you back up to speed. So in the first video, we'll just be going over vector spaces. So what is a vector space? Well, a vector space is a set V over some field F, which has elements that we call vectors. And there are two operations. There's addition of vectors, and there's scalar multiplication between a scalar from our field and a vector. We see that visualized here. In this visual example, we're working with a vector space being the plane, and you can add vectors in the plane R2, and likewise, you can scale vectors in R2, multiplying them by a constant, which will either extend or shorten them. So now, let's give the formal definition. A vector space over a field F is a set V along with operations addition, which is mapped from V cross V to V, given by U comma V maps to U plus V, and scalar multiplication, a function from the field cross V to V, given by C comma V maps to C dot V, or in other words, C times V, satisfying a number of properties. I won't go through all of the properties in detail. I'll just, use the phrase, and if you want to, really take the time to parse them in detail, feel free to, of course, pause the video. So properties are associativity of addition, commutativity of addition, the existence of an additive identity, the existence of additive inverses. Then further, there are additional properties, associativity of the scalar multiplication, the existence of a multiplicative identity, the fact that multiplication distributes over vector addition, and the fact that multiplication distributes over field addition. So these are all of the 8 properties necessary for a definition of a vector space. Some examples include first, the vector space, the reals, where we take the scalars also from the reals, and addition and multiplication are the usual addition and multiplication that we've worked with since elementary school. The next example is R to the n, n-dimensional Euclidean space, where again, the scalars are the reals, and addition and multiplication are defined coordinate-wise. So what do we mean by coordinate-wise? Well, when we have a higher dimensional vector, we can write it out in coordinates. Like here, we have vectors u1 through un, or the vector u1 through un, and another vector v1 through vn. So these are two vectors inside n-dimensional Euclidean space. So that means each u sub I and v sub I is a single real number. And we add these two vectors by just adding the real number in each coordinate. Similarly, if we take some scalar c, we multiply c by a vector by multiplying c by the real number in each coordinate. this can be generalized outside of Euclidean space to work for any field. So if you fix any field f, you let v be f to the n, where addition and multiplication are defined coordinate-wise as above. And most of the vector spaces we will be working with in this course are of this form in example 3. One common field that we'll be working with very frequently is Z2, which is also denoted or read Z mod 2Z. This field consists of the set 0, 1 with operations addition modulo 2 and multiplication modulo 2. So again, this is a very important field in topological data analysis, and we'll see why in a few weeks. Basically, this field is what's used in most applications, and there are both computational efficiency and interpretability motivations for doing so. And we'll talk about that more in a few weeks. So now we've reviewed vector spaces. Let's briefly talk about direct sums. So you might recall there are two different notions of direct sums, external and internal, but they're going to be isomorphic here. In this case, we're going to just talk about external direct sums. Most of what we do in this course involving direct sums can be viewed through the lens of an external direct sum. So let's review the definition. If V and W are vector spaces over a field F, then the external direct sum, V plus W, is a vector space where the set is just the direct product of V and W, and the operations are addition and scalar multiplication, both coordinate-wise, as we've seen previously today. Example for F a field, f to the n, which was noted earlier, is a vector space given by the external direct sum of n copies of the field f. Next, a very important descriptor of vector spaces is a basis. So for the definition, a basis B of a vector space V over some field f is a subset of vectors which satisfies two properties. So first, a linear independence property. This says that for every finite subset, V1 through Vn of the basis, if we have some linear combination, so C1 V1 plus C2 V2 plus ... through plus Cn Vn, if such a linear combination equals 0 for some scalars C1 through Cn in our field, it must be the case that C1 through Cn are all equal to 0. In other words, we can't add the vectors in a basis in any non-trivial way and get back to 0. The second property is called spanning. So this property states that for every vector v in our vector space, there must exist some scalars C1 through Cn and vectors V1 through Vn in our basis such that V can be written as the linear combination of these scalars and vectors. So V equals C1 V1 plus C2 V2 plus ... through plus Cn Vn. Standard example, if V is f to the n, then the following is a basis for V, where each vector has 1 in a single coordinate and 0 in all other coordinates. And we denote by E sub I the basis element with 1 in precisely coordinate I. So this would be E1, E2, so on and so forth. And this last vector would be E sub n. If V has a basis B with n elements, where n is some finite number, then we say that V is an n-dimensional vector space. It's a good exercise to do after we've seen some of the later recitation videos in this week so that you have all the necessary techniques. It's a good exercise to show that this is a well-defined notion. What I mean is you want to show that if V has two different bases, say B1 and B2, then B1 and B2 must have the same number of elements. So next and lastly for this video, we'll give the definition of a linear subspace. So a subset W of a vector space V over some field F is a linear subspace if W with the operations, meaning addition and scalar multiplication, from V restricted to W is a vector space over F. So that's a formal definition. An equivalent definition, which is oftentimes stated as a definition, so I'll state it here as well, is that W is a linear subspace of V if W is a subset of V, and for all scalars, A and B in the field, and vectors U and V in W, A times U plus B times V is also in W. So here are a couple examples. If M is less than or equal to N, then M-dimensional Euclidean space can be viewed as a linear subspace of N-dimensional Euclidean space by embedding V1 through Vm, going into the first M coordinates, and then just tacking on zeros at the end of each vector. Another common linear subspace is if we have W, some set of vectors, inside V, you can define the span of W to consist of all linear combinations of vectors in this set. And if you do so, then you can show that the span of W is a linear subspace of V. So these are some important notions and examples regarding vector spaces. And in the next video, we'll talk about how we relate different vector spaces via linear transformations. So I will see you all then.